So two nice properties that a field has are, these are kind of nice things that we take for granted that we've already seen fail in general, but let me explain. So if f is a field, then it has the following two properties. And the first is the zero multiplication property, that if a times b is zero, that means that a is zero or b is zero. And the reason is that, first of all, if a is zero, then we win. There's not much to do. But if a is not zero, then what we can do is we can multiply both sides of this equation by a. Here by multiply, I mean apply that operation star. And if I multiply both sides by a inverse, on the left side, I can use associativity to regroup the parentheses. On the right side, I can use the fact that's not as obvious as you might think, but it's not hard to prove. Anything times zero is zero. That seems obvious, but you need to remember how general these objects are that we're working with. And so think of the weirdest ring that you could possibly think of with whatever operation you can think of. It turns out that any object times zero is still zero, okay, in a suitable sense. So I'm not going to prove that, but that's something that you would do in an algebra class. Now, a inverse times a on the left side of this equation is just the multiplicative identity, because we know that fields are the rings where every non-zero element has this multiplicative identity, or has a multiplicative inverse, I mean. And the multiplicative inverse of a times a is just the multiplicative identity. That's what we mean by a multiplicative inverse. And of course, the multiplicative identity times b is just b. So if a is not zero, then b is zero, and we win. Okay, so fields have this nice property that if you take the product of two terms and you get zero, then one of them must be zero. I forget, again, whether this was on an exam or on a homework, but this is something that you've actually seen is a property of primes. You saw that there exist, I think this was on an exam, but there exist what are called zero divisors if and only if we're working mod a composite number. So this type of thing fails if we're working over, say, the ring of integers mod 12. So in Z12, just for example, you could have, let's see, 3 times 8 is 0, because 3 times 8 is 24. 24 mod 12 is 0. So here you have two numbers that when you multiply, these are two non-zero numbers, so that when you multiply them together, you get 0. That kind of weird existence of zero divisors happens only when we're not in a field. Okay, if we are in a field, there are no zero divisors. So that's another way to think about the existence of zero divisors if and only if that modulus is composite exercise that I had you do, I think, on the last exam. One other property that's nice, and I'm not going to say too much about this, but it turns out that if you have a polynomial, say x squared plus 4x plus 2 is congruent to 0 mod, let's say 11, it turns out that there's going to be at most two solutions to this. And the reason why I say at most two solutions so first of all, I didn't pick this very carefully. Maybe there's only one solution and you have a repeated root. Maybe there's no solutions. I haven't picked this carefully at all to know whether or not there's solutions or not. But you know that there's not going to be any more than two solutions because this is a second degree polynomial. And importantly, the ring of integers mod 11 is a field. And it turns out that that's another property of fields that we take for granted. It turns out that if you have a degree d polynomial over a field, then that polynomial will have at most d zeros. In other words, you can factor it into at most d terms, including multiplicity. So maybe it's the same term d times, maybe maybe it's d different terms, it doesn't matter, but you can have at most d solutions. Now, if you were to work, again, another exercise that we talked about, if you were to work over the integers mod 8, it turns out that that's no longer true. So x squared congruent to 1 mod 8 actually has 4 solutions, and that's 1, 3, 5, and 7. Whenever you square those, you get 1 mod 8. The reason why that's allowed is that the integers mod 8 are not a field. So you don't have that nice property that a degree 2 polynomial has at most 2 solutions. And in this case, it had 4. There's some things that you can say about the degree and how to count the number of solutions, but the basic fact of having at most d solutions for a dth degree polynomial is only true over fields. So if you have a set that's not a field, that could be false.